This is a lecture on a few challenging problems. The problems will consist of calculation of momentum, change in momentum, impulse, the relationship between impulse and change in momentum, and it will cover the conservation of momentum. Remember, take some copious notes and hand them in for extra credit, and have some paper and pencil ready for you to take notes. A cart weighing 24.5 newtons is released from rest on a 1-meter ramp, inclined at an angle of 30 degrees as shown in the figure below, which is on the next slide. The cart rolls down an incline and strikes a second cart weighing 36.8 newtons. Calculate the speed of the first cart at the bottom of the incline. Okay, so we've got to do a calculation given a mass on an incline. Sounds familiar. No mention of friction, so the FP, which is that portion of the weight that's parallel with the ramp, is going to actually equal the net force. There's nothing to subtract. There's nothing contrary to that FP. So FP will be the net force. Then I divide the net force by the mass, and that will equal the acceleration. And then I want you to choose, before we get there, I want you to choose which motion equation is going to relate final velocity, initial velocity, acceleration, and distance, which remember is given as 1 meter. Now, the FP equals FW sine theta. That is given in the equation there. FW1, or the weight of cart 1, is 24.5 kilograms. That's going to be used to calculate FP. FP is going to be, and that's going to be M1. The mass of cart 1 is 2.45. I'm dividing by 10. It's just easier. If it was 9.8, it would be 2.5. You'd get a value that's a little different, but in terms of 2 or 3 Stephenson figures, it's really not much. There's no friction again, so FP equals F net. And let's look and see what else is going to come up. What else do you see that might need some? There's the equation for acceleration, FP over m, because there's no friction, so FP over m is the same as F net over m. So FP is going to be FW1 sine theta, and then divide that by the mass, which is 2.45, and that will be the acceleration that the cart experiences due to the net force that's calculated to be FP. So it's going to be FW1 times sine 30 degrees, and then divide by the mass. And there you have the expression. Now, what is the acceleration going to be given that data? What is the acceleration going to be given that data? So what is, the acceleration is 5. So now, what do we have? What equation are we going to use to calculate the final velocity? Which one of those 3 equations we're going to use? That's the one where it's going to be VF squared equals VI squared plus 2 delta D, or the change in distance. That's going to be reduced to root 2AD, and that's going to be root 10, and root 10 is 3.13, very good, 3.13. So that's going to be the velocity of the first cart. So what momentum is the first cart going to have when it reaches the bottom? Well, it's going to have, there's the material that we've discussed that was either given or calculated. If the 2 carts stick together, with what initial speed will they move along? That's a little deceiving because it's actually going to be a final speed that you're actually going to calculate. You're going to calculate the VF for the system because 1 and 2 are going to stick together. So we know what V1I is, that's 3.13. We know what M1 is, that's going to be 2.45. Divide through by the sum of the masses, and you get the final velocity of the system. I use the property of symmetry to kind of flip-flop them and then divide through. So it's going to be the M1 VI, which is the first car at the bottom of the ramp, and that's the values that you're going to plug in there. And then the answer will be, wait for it, can you do it before it comes up? I challenge you. You can put it on pause. 1.25. You can see it's gaining mass and losing velocity, and that's what it should be. And remember, it's gaining significant mass relative to it because it's gaining 3.68, which is quite a bit larger than the 2.45. Number 2, a 0.24 kilogram volleyball approaches Tina with a velocity of 3.8 meters per second. Tina bumps the ball, giving it a speed of 2.4 meters per second, but in the opposite direction. What average force did she apply if the interaction time between her hands and the ball was 0.025 seconds? Well, it says 0.24 kilogram volleyball approaches Tina at 3.8 meters per second. So the ball is applying a force on Tina, and Tina is applying a force on it. The bounced ball is going to be going at negative velocity, and the original velocity is 3.8, so that's going to be a positive force. So Tina's going to apply a negative force. So it's going to be the change in velocity divided by time, which is the same as I, impulse equals change in velocity. Impulse is Ft. So divide change of momentum divided by t, and that gives you the answer. So it's going to be, you can see how it's going to be negative 2.4 meters per second minus 3.8, and that's going to be a negative value, so it'll be negative 60. It'll be negative 60. Number 3, a 0.145 kilogram baseball is moving at 35 meters per second when it is caught by a player. A, find the change in momentum of the ball. So the ball is going to go, its initial velocity is 35 meters per second, and it'll go down to 0. So it'll be 0 minus 35. So it's going to be a negative momentum. That's very important if you want to calculate forces involved. If you have a negative momentum, a negative change in momentum, then the impulse is going to be negative and the forces involved will be negative. So it's going to be 0.145 times negative 35, because 0 minus 35 is going to be negative 35. So 0.145 times negative 35 is going to be negative 5.1 kilogram meters per second. Kilogram meters per second. Now, if the ball is caught with the mitt held by a stationary position, held in a stationary position, so that the ball stops in 0.050 seconds, what is the average force exerted on the ball? What is the force exerted on the ball? So what is the force exerted by the mitt on the ball? The ball is going to exert a negative force, and the mitt will, or the glove will exert a positive force. So we start with the change in momentum, which is negative, and that's going to equal the force exerted by the ball times the impact time, and that will be 0.05. So it's going to be the change in momentum, which is negative 5.1, divided by 0.05 seconds, and the answer will be a negative force. And now calculate that, and you'll see that it's going to be about 100-ish. It's going to be about 100-ish, 100 newtons. And that's exactly 100. So, because 5 divided by 5 is 1, and then you have moved it over 2 places to the right, and you get 100. So it'll be negative 100. But it says, what is the average force exerted on the ball? If the ball is caught with a mitt held in a stationary position to the ball, what is the average force exerted on the ball? Well, the ball, it's going to be positive. The ball is going to exert negative, and the mitt exerts a positive. Now, if instead the mitt is moving backwards so that the ball takes 0.5 seconds to stop, what is the average force exerted by the mitt on the ball? So instead of having an impact time of 0.05, it's going to be 0.5. So it'll be 10 times less. So instead of 100, it'll be 10. Now, you just have to make sure that you have your signs correct. So the ball will exert a negative force on the mitt, and the mitt will exert a positive force on the ball. So the force exerted by the ball, because that's the way the problem is written, is going to be calculated in the exact same way that we calculated for the impact time of 0.05. So you're just going to get different values because it's 0.5 instead of 0.05, but they'll differ by a magnitude of 10. So you have negative 5.1 divided by 0.5 instead of 0.05. So how many halves are there in 5? Well, there's 2 halves in 1. 2 times 5 is 10, so it'll be negative 10 newtons. And that's the exerted by the ball. And exerted by the mitt, it will be positive 10 newtons. Because that's going to be exerted on the ball, not by the ball, on the ball. Okay, and that looks like that's the end of problem 3. A nitrogen molecule with a mass of 4.7 times 10 to the negative 26 kilograms, moving at 550 meters per second, strikes the wall of a container and bounces back at the same speed. What is the impulse the molecule delivers to the wall? Now, even though you're going to have, it's bouncing, so you're going to have a change in velocity of 1100 meters per second, it's a very small mass. So the final is going to be negative 550. So it'll be negative 550 minus a positive 550, which is negative 1100. So, but the value is going to be fairly small. Now, what is the impulse the molecule delivers to the wall? Well, that's the impulse. It'll be negative. The wall will deliver a positive impulse, and the wall will deliver positive, and the molecule will deliver a negative. So the impulse the molecule delivers to the wall is negative 5.2 times 10 to the negative 23 kilogram meters per second. And the impulse the wall delivers to the molecule is positive 5.2 times 10 to the negative 23 kilogram meters per second. Now, B, if that's true, if there are 1.3 times 10 to the 23 collisions each second, what is the average force on the wall? So the average force on the wall will be same general equation, but we're going to multiply by that many collisions. See if you can do this. Remember, you have mass times the change in velocity divided by the change in time. So there's that many collisions per 1 second. So the time is going to be 1 second. So for all the collisions, the force is going to be calculated the same way it was for part A. It's going to be the mass times the change in velocity divided by the change of time, which we said is 1 second. So that's the same thing we did in part A, but this time we're going to multiply that value by 1.5 times 10 to the 23 collisions. It's almost a quarter of a mole of collisions each second. So this is the exact same calculation we did, with the exception that we're multiplying it by 1.5 times 10 to the 23rd. And the force is going to be equal to, the way the problem was written initially, negative 7.8 newtons. So we can say two things. The force on the wall delivered by the molecule is going to be negative 7.8 newtons, and the force on the molecules delivered by the wall would be positive 7.8 newtons. So, problem 5 is about an accident, accident physics. A car moving at 10 meters per second crashes into a barrier and stops in 0.05 seconds. There is a 20-kilogram child in the car. Assume that the child's velocity is changed by the same amount as that of the car, and in the same time period. What is the impulse needed to stop the child? What is the impulse needed to stop the child? Well, it's simply going to be equal to the change in momentum, which is simply going to be the mass times the velocity. So it's going to be 20 kilograms times the quantity, negative 10, so it'll be 200 Newton seconds, or 200 kilogram meters per second, negative. And then it says, then it's going to say, well, what force is used to do that? Well, if there's no airbag, then it's going to be, 0.05 seconds, or even shorter than that. Could be as much as 1/10,000th of a second. So that's going to be, you're going to take your change in momentum, which is negative 200, or the impulse, which is negative 200 Newton seconds, or kilogram meters per second, and divide through by 0.5 seconds, and you will get, how many times does 5 go into 20? So it'll be something with 4 somehow. So let's change the time frame so this goes a little bit more quickly. So this is going to be the same problem we just did, with the exception that we're dividing it by 0.5. So it'll be 200 divided by 0.5 seconds, which is negative 4,000 newtons. So that's significant. So you can see why there are many different types of safety equipment in a car, from crumple zones to seat belts, etc. What is the approximate mass of an object whose weight equals the force in part B? What is the approximate mass of an object whose weight equals the force in part B? Well, my mass is 100 kilograms and I'm 1,000 newtons, so do the math. If it's going to be 4,000 newtons, it'll be 400 kilograms. So a pretty significant mass, and that's why people get injured. And people should slow down, but no one ever does. If more people had a basic understanding of physics, we wouldn't have as many accidents and as many injuries on the roads. So I think that might be it for that problem. Let's check it out. Let's wait. And so I'm not sure why that did that, but it's 4 times 10 to the third newtons divided by 10 is going to be 400 kilograms. So could you lift such a weight in your arms? I couldn't. Can you lift 4 of me, your teacher? I don't think so. So it would be almost impossible to, if you had that person on your lap, you couldn't possibly save that person. So it would be, the answer would be no. Why is it advisable to use a proper restraining seat rather than hold a child on your lap? 20 kilograms is not that much. Toddler, maybe a little bit heavier than a toddler. You would not be able to protect a child on your lap in the event of a collision. So pretty significant. Okay, on to the last problem. A 95 kilogram fullback running at 8.2 meters per second collides in midair with a 128 kilogram defensive tackle moving in the opposite direction. Both players end up with 0 speed. Identify the before and after situations and draw a diagram of both. Okay. The free body diagram, although it wouldn't be quite this well done, would be the fullback running from left to right and the defensive tackle from right to left. So the before information relative to the 2 football players will be the mass of the fullback is 95 kilograms. The mass of the defensive tackle is 128 kilograms. The velocity of the fullback, he is running at 8.2 meters per second. There is no velocity given for the velocity of the defensive tackle. However, the defensive tackle will be moving, but we don't know what it is. We're going to have to calculate that. Now, the after situation will be, they'll both be together, so the velocity of the fullback plus defensive tackle will be 0. That'll be the after value. So the after would consider the mass of both, and then the would be 223 kilograms, and then the velocity would be 0. Now, what was the fullback's momentum before collision? Well, it's 95 times 8.2 meters per second. Now that's going to be the same as the change in momentum. So I'm doing both together. So what was the change in the fullback's momentum? Well, the momentum of the fullback is 780 kilograms meters per second. And the change in momentum is negative 780 because it's final minus initial. So the change is negative 780 kilogram meter per second. So the change is going to be negative 780 kilogram meters per second, and that's for the fullback. So even though the original momentum was 780, the final momentum was 0, so it's 0 minus 780, which is a negative 780. Now, what was the change in the defensive tackle's momentum? Well, it's got to be the opposite. It's going to be positive. Now, a note about why it's positive, and this is crucial. Well, it's going to be positive because it's got to be equal and opposite to the fullback. However, it's going to be a change. So it's going to be final minus initial. So it's going to be 0 minus a minus value. So when it says, well, what was the defensive tackle's original momentum? Well, it has to be negative because, again, it's final minus initial. So it's going to be 0 is the final. 0 is the final for both. So it's 0 minus a minus value. It can't be 0 minus a positive because the other is positive. So it's going to be 0 minus a minus value. So that's very important, and you should be getting sophisticated enough to make sense of this. So the change in momentum is positive because it's going to be 0 minus a minus, and the defensive tackle's original momentum must be minus because it has to be 0 minus a minus because the fullbacks was positive, so he has to be negative. He's going the other direction. Well, why does it have to be negative? Why is it negative? Well, we're going to look at that right now. It says, how fast was the defensive tackle moving originally? Well, the defensive tackle, remember, the original velocity of the fullback was positive. Do you remember that? Now, we're saying that the momentum was negative for the defensive tackle. The momentum is negative. So you can see here the velocity is also negative. So the reason the momentum is negative is because the velocity is negative. So it should all pretty much make sense now. Let me know if you have any questions and ask me in class. Quizzes next week. Have a great weekend and goodbye.